Welcome back as we move on to describe electrical checks. The first check that we shall perform is to test for continuity between the windings. Ensure that the multimeter is set up for low resistance measurements as previously discussed. Connect one of the test leads onto the first slip ring. Then probe the remaining 2 slip rings, recording the ohmic resistance after each measurement is observed. All resistance readings must read within 5%, indicating that the windings are balanced. Next, we will test the insulation resistance from each winding and the brush gear to earth. To begin, connect one test lead to the rotor shaft and the other to each slip ring in turn, each time testing the insulation resistance. All the insulation resistance measurements recorded must be greater than 0.5 megohms to be acceptable. When the motor has been assembled and the brush is lifted away from the slip rings, test the insulation resistance between each brush holder and the frame. Once again, the readings obtained must be greater than 0.5 megohms. Now we move on to the mechanical checks. First, check the surface of the slip rings for excessive, uneven wear. The surfaces should also be free from grease, oil, or grit. Moving to the brush gear, check the pigtails for loose or damaged connections. Check the length of each brush for excessive wear. They should not be worn beyond the specified limits. Ensure that the brush holder is clean and that the brush is able to move freely within the brush holder. Check the spring pressure of the brush holders. A weak spring will cause brush bounce, resulting in a poor electrical contact with a slip ring. Examine the tip of each brush. A properly shaped tip will ensure maximum contact with the slip ring. Check the alignment of each brush with its respective slip ring. Correct brush position will ensure that the brush runs in the center of the slip ring. This completes the mechanical tests. Let us now recap by mentioning 2 important points concerning 3-phase induction motors. A 3-phase cage induction motor is simply constructed, efficient, and cost-effective with fixed speed and torque characteristics. The slip ring motor, with its wound rotor, allows the user to control the start current and speed and torque characteristics by connecting preset values of resistance in series with the rotor windings. This concludes Module 2. Join us again in other programs where you can learn more about the basic operating principles of AC and DC machines. The producers and distributors of Tech AV training programs welcome you to the 3rd module in the series AC and DC Machine Fundamentals. This series of programs has been designed to help you understand the basic operating principles of both AC and DC motors and generators. In this module, we shall overview the DC machine, and you will learn about the key components and their functions, the operating principles of a motor and generator, and basic electrical and mechanical test procedures. As a motor, the DC machine is most suited to driving a load when it is required to control the speed of the load, for example, in lifting and traction machinery. Likewise, as a generator, the machine will produce a direct current output depending on its speed and excitation. In its most basic form, a DC machine consists of the following key parts, namely a rotating part called the armature, a stationary part called the stator, which contains the yoke, the poles and field windings, two end shields fitted with bearings which support the armature, and a set of brushes held in position by brush holders collectively called brush rigging. Let's discuss the construction and function of each of these parts in detail. We begin with the armature. A typical armature incorporates the following components, namely a core comprising a number of sheets of high-grade electrical steel called laminations, which are pressed onto a steel shaft. Next, the armature windings, which consist of a number of evenly distributed coils of copper wire which are wound into the slots in the core. The ends of the armature coils are connected to the commutator, which is attached to the end of the shaft. The commutator consists of a number of copper bars or segments which are insulated from each other and the shaft. Next, the brush rigging. On all DC motors or generators, current must be conducted to or from the armature windings via the commutator. This is achieved by a set or sets of carbon brushes which ride on the commutator. Finally, the armature shaft. One end, called the drive end, is used to transmit power to the load, and the opposite end is called the non-drive end, which generally supports a cooling fan. We move on to the static part of the machine. It is composed of a number of high-resistance steel plates called laminations, which are bolted together and pressed into either an aluminium or iron frame. Coils of copper wire are fitted to the core, forming north and south poles when direct current is connected to them. The main poles produce the main magnetic field, and the interpoles produce a magnetic field which counters the effects of armature reaction. After the break, we will explain the basic operating principles of a DC motor. Welcome back as we discuss the operating principles of a typical two-pole DC motor. To begin, let's examine the behavior of these two permanent magnets. If the like poles are brought together, they repel each other, and if the unlike poles are brought together, they attract each other. Using these principles of magnetic attraction and repulsion, we can explain the operation of a basic two-pole DC motor. In this demonstration, two electromagnets and their respective pole pieces produce the main magnetic field and represents the static part of the motor. The coils are wired to create the main magnetic field when connected to a direct current supply. With the aid of a compass, we are able to see the direction of the field at each pole face. The needle indicates that the path of the magnetic lines of force extend from a north pole to a south pole and back to the north pole via the iron frame or yoke, which completes the magnetic circuit. Now, to the main field system, we add an electromagnet which is free to rotate, called the armature. This simple two-pole armature has a set of windings which are energized via brushes which ride on a two-segment commutator. Current flowing in the armature windings produces a magnetic field, and a pole is formed at each end of the armature where the magnetic flux is concentrated. When energized with DC power, the main poles and the armature poles attract and repel, producing forces which turn the armature. The commutator and brushes, acting like a mechanically operated reversing switch, maintain the correct polarity of the armature poles to sustain rotation. To ensure that the motor runs efficiently, the switching position or point of commutation must be correctly set. This is achieved by adjusting the position of the brush gear for minimum sparking and maximum speed. Let's now discuss changing the direction of rotation. This can be achieved by swapping the supply to the main winding, or, as demonstrated, by swapping the supply to the armature. We move on to discuss back EMF or counter EMF. Back EMF is the voltage induced into the armature windings as they turn within the main magnetic field. Since the induced EMF opposes the applied voltage, it is called a counter EMF or back EMF. When driven as a generator, the back EMF produced by the armature turning in a magnetic field produces the DC output voltage. When connected as a motor, this back EMF affects the amount of current flowing in the armature. In this demonstration, we can see how the back EMF affects the current in the armature circuit. At switch on, the current flowing into the armature is a maximum, but as the speed of the armature increases, the armature current falls as the back EMF increases. The armature current is clearly determined by the difference between the applied voltage and the back EMF. This concludes our discussions on the basic operating principles of the DC motor. After the break, we will discuss types of DC motors. Welcome back. We shall now overview the types of DC motors which are classified according to the method of connecting the field windings. We begin with the series wound DC motors. The motor is ideally suited for traction applications where it is required to start under heavy load, for example in a locomotive. The series field, which consists of a small number of turns of thick insulated copper wire, is connected in series with the armature. As a result, the field strength is proportional to the armature current, producing a high torque characteristic. Since the back EMF generated in the armature is insufficient to limit the speed, a series motor is not a constant speed machine and will speed up rapidly as the load is removed. Next, we look at the shunt wound DC motor. This type of motor has a relatively constant speed characteristic and is typically used to drive a fan or conveyor. The shunt field is very different from the series field and consists of a great many turns of fine gauge insulated copper wire wound on the main poles of the stator. The shunt field winding is connected in parallel with the armature or shunts the armature. The machine is able to maintain a fairly constant speed since an increase in load will result in an increase in the armature current for a given shunt field current. Finally, let's look at the compound wound motor. The compound motor is a combination of the series and shunt motors and combines the best features of both, having a high starting torque with a fairly constant speed characteristic. The field system comprises a series winding and a shunt winding field, which lie next to each other on the main poles. The shunt field, with its many turns of fine wire, is first fitted, followed by the series field. Usually, the motor windings are configured in a cumulative compound long shunt type of connection. This means that the fields combine, and should the load be suddenly removed, the motor will not overspeed. Like the series and shunt motors, the direction of rotation can be changed by swapping the armature connections. To conclude this section, let us remember that when driven by a prime mover, our DC motor becomes a DC generator, whose output characteristics are determined by the configuration of the windings. For example, a series generator will generate a constant current output. A shunt generator will produce a constant voltage output, and a compound generator will generate a constant voltage under varying load conditions. After the break, we will continue with electrical test procedures. Welcome back. In this section, we will demonstrate electrical test procedures that are performed after a motor or generator has been serviced, repaired, or is simply being tested for integrity. We will demonstrate, using generally accepted procedures, how to test the three main electrical parts of the motor, namely the series winding, the shunt winding, and the armature circuit. Before attempting any electrical tests, ensure that the motor is isolated from the main supply and that you adhere to the safety procedures laid down by your company and the relevant code of practice. Access to all electrical components is made in the terminal box. All the electrical components are connected inside the box to a terminal block. A wiring diagram is usually affixed to the inside of the lid and will assist in identifying the designation of the various binding posts. The first series of tests we shall perform are called the continuity tests. In each case, we shall measure the ohmic resistance of the windings using a good quality analog or digital multimeter. We suggest that you have an electrical checklist to sketch the connections and record the meter readings in addition to your comments. Begin by setting the multimeter to the ohms position. Clip one of the test leads to the top left-hand post. Probe all the remaining posts, moving from left to right across the terminal block until a reading is obtained. Record the position of the connected posts and the resistance readings on the checklist. Now move the lead to the next post along and repeat the procedure, noting the value of the resistance measured and the position of the connected post. Do this until you have mapped all the posts. As a rule, the series winding will show the lowest resistance, the armature circuit, which will measure slightly higher, and the resistance of the shunt winding will show the highest resistance. Now we move on to discuss insulation resistance testing, where we shall test for a breakdown in the insulation resistance between the series and shunt windings, and test the insulation resistance between the windings and the frame of the machine. We begin by measuring the insulation resistance between the field windings. For this, we use a high-voltage insulation tester, or mega. To prepare the instrument, set the output voltage of the mega to 500 volts and select the meg-ohm range. Clip the test lead onto one end of the series winding and connect the other lead to one end of the shunt winding. Press the test button and note the reading on the meg-ohm scale. It must read greater than 1 meg-ohm. A reading less than 1 meg-ohm indicates a possible leakage path between the two windings. Now move the test lead to the other end of the shunt winding. Test the insulation resistance again. The reading must be greater than 1 meg-ohm to be acceptable. Remove the test lead from the series winding post and connect it to the other end of the series winding. Once again, test the insulation resistance between the windings and ensure that the reading is greater than 1 meg-ohm. Finally, remove the test lead from the shunt winding and connect it to the opposite end of the shunt winding. Test the insulation resistance again between these windings. Record the resistance readings and conclusions on the checklist after each measurement is taken. Next, we test the insulation resistance between the windings and the motor frame or earth. Begin by attaching one of the test leads to the frame of the motor. A good electrical earth point is usually available inside the terminal box. Then, with the other test lead, probe and test the ends of each winding and the armature circuit, which includes the interpoles and the brush circuits. Record each measurement and your comments on the checklist. To meet acceptable standards, all the resistance readings obtained must be greater than 0.5 of a meg-ohm. Any reading less than half a meg-ohm suggests a possible insulation breakdown in the electrical system to earth. The final set of electrical tests concerns the circuits contained in the armature. As a rule, the armature circuit consists of the armature windings, the interpoles, and the brushes. Let's first look at the armature itself. We will test the armature coils for an open circuit or short circuit condition. Mark a starting point on the commutator with an erasable marker pen. Then measure the resistance between each adjoining pair of commutator bars. The meter readings should all be similar in value. 0 ohms will indicate a shorting coil, and a high resistance suggests that the coil is open circuit. Continue testing in this manner until you return to the starting point. Update the checklist with the test results. This completes the continuity tests. Now we will test the insulation resistance between the windings and earth. Power up the insulation tester to read continuously on the 500 volt range. Connect one lead to the armature shaft and then probe each commutator bar in turn. If there is no leakage or direct path to earth, the readings will be greater than 0.5 of a meg-ohm. Update the checklist before commencing the next test. Now to check the brush gear. The requirement is to test the insulation between each brush holder and earth. With the brushes lifted away from the armature, measure between each brush holder and earth. The readings must be greater than 0.5 meg-ohms to be acceptable. Having established that the brush gear is clear from earth, we can test the interpole windings. To isolate the interpole winding from the rest of the armature circuit, we must place a short across the armature or lift the brush gear away from the commutator. With the shorting link in place, measure the continuity of the interpole winding by connecting the meter across the armature terminals on the terminal block. As a rule, the winding resistance should be slightly less than the resistance of the series field winding. Finally, we must test each end of the interpole winding to earth to determine the insulation resistance. Connect one end of the insulation tester to the frame of the machine and probe each terminal of the armature circuit in turn, noting the meter reading. The resistance measured must be greater than 0.5 meg-ohms, which indicates that the winding is acceptable. After the break, we'll discuss the mechanical test procedures. Welcome back, as we next discuss mechanical checks that should be performed on a motor. We begin with the bearing test. To check the bearings, rotate the motor shaft by hand and listen carefully for any abnormal noises which may indicate worn bearing surfaces. Then, test the shaft for lateral play by moving it from side to side and in and out. There should be no appreciable movement if the bearing is in good order. Next, perform a visual inspection of the shaft and keyway. Where applicable, check the condition of the keyway for excessive wear or damage. Then, using a dial gauge indicator, check the condition of the shaft to ensure that it is not bent. There should be no deflection beyond approximately 0.02 millimeters under normal circumstances. Next, examine the frame